the homework from page 463. We're finding the volume of solids revolved about an axis other than the x or the y-axis. So let's just kind of jump into it. In number 11C, you have the square root of x, y equals 0, x equal to 4. And I've already sketched the region that we are revolving. Just in case you're in doubt, the region that we're revolving is this region right here that I've highlighted with the green. Now we're revolving that region about the line x equal to 4, which is a vertical axis. So since this is a vertical axis, it's parallel to y-axis, we will be in terms of y. Remember, when you revolve about an axis parallel to the y-axis, you are in terms of y. Since this region, the green region that I highlighted, since it's flush all the way to the axis of revolution, if you look at the red dotted line, this is the axis of revolution, and the region that we're revolving is completely flush to that line. There's definitely not going to be a hole in this revolution, so this would be no hole, which indicates that I'm only going to have an R, or I'm going to have one radius. Now, as we've talked about in class, the radius always starts at the axis of revolution and it travels to the curve. So this segment right here is the radius that I'm trying to define. However, it's difficult to define that radius without using, in this case, the y-axis. So I'm going to take that segment all the way over to the y-axis. Now that segment right there is definitely longer than my radius. The length of this segment from here to here is 4 units. Now bear in mind, that is not the length of my radius. The length of my radius is just this part that I'm coloring in red. So if that's the piece of the segment that I want, and the segment that I'm trying to eliminate, I'll highlight in this blue, I'm trying to eliminate this portion of the segment. The whole thing is 4 units long, and I'm trying to eliminate that little blue section. Now the little blue section is defined, it is the distance from the y-axis to the curve, and it has to be in terms of y. So I'm going to take this function right here, y equal to square root of x, and I'm going to turn it into x equal to y squared, because I need the function in terms of y. So that little blue region right there that I've highlighted, that distance is y squared. So the length of my radius is 4 minus y squared. So I will have the integral. Remember, we're revolving, so we're making circles. The area of a circle is pi r squared. We're in terms of y. The bounds will be y values. So the lower bound, we're going to sweep the area from low to high. So the lower bound would be a lower bound of 0. The upper bound would be right up here. So it is the y value when 4 is substituted in here. So the square root of 4 is 2. So I'm going to collect the area from 0 to 2. Then I'm going to take my radius, which is 4 minus y squared. I'll take it maybe one step further. That would be the integral from 0 to 2. I'm going to square the binomial. 16 minus 8y squared plus y to the 4th dy. I'm going to find the antiderivative, which would give me pi 16y minus 8y cubed over 3 plus y to the 5th over 5. From 0 to 2. I'm going to evaluate that at 2. Fortunately, the 0 will go out, and then I'll get my answer. But the big deal here is being able to identify the length of that radius and recognize that you have to take the radius all the way over to the axis and then eliminate the part that you don't need. And that's true whether you're in terms of x or whether you're in terms of y. All right, let's take a look at 11D. It is the same region, the same functions, y equal to the square root of x, x equal to 4, x equal to 0. We're revolving the same region, but this time notice that there is a big space in between the curve, or the region that we're revolving, and the axis of revolution. So that space is right in there, and that's what's going to generate a hole. So let me get rid of that so that you don't think that's what we're revolving. Make a little repair job here. Put that back, put that back. Okay, so there's definitely going to be a hole in this thing. So there's going to be, and also, since our axis is a vertical axis and parallel to the y-axis, we're going to be in terms of y. We're going to have a big R of y, and we're going to have a little r of y. Big R of y is the distance from the axis of revolution to the outer curve. So this would be a representative radius of big R of y. Now, just like we said in the other problem, we have to take that segment all the way over to the y-axis. So the length of that entire segment is 6 units long. But keep in mind, just like before, the only part of the segment that we're really going after, the radius, is this distance right here, which means I'm going to have to eliminate the distance over here. Now that blue distance, again, is the distance from the y-axis to the curve, which is y squared. Remember, we solved the equation in the last problem for x, and this distance is y squared. So the length of my big R is 6 units. Subtract out the y squared. The little radius, or little r, is the distance from the axis of revolution to the inside curve. Now this is easy to define because it's a vertical segment and the distance from 4 to 6 is always 2 units. So little r is 2 all the time. We're going to collect the area, pi out front. We're still going to go from 0 to 2 because we're in terms of y. Big R would be 6 minus y squared squared minus little r, 2 squared dy. Cleaning that up will give me, oops, I haven't found the antiderivative yet. Let's get rid of that. Back up. So I have pi from 0 to 2. Square that thing, and that'll give me 36 minus 12y squared plus y to the 4th minus 4 dy. I'll combine my like terms, the 36 take away the 4. I'll find the antiderivative and do the substitution and the arithmetic. Again, the reason I'm doing these videos mainly is to help you to figure out the length of that radius, because that can be the challenging part of these problems when we're revolving around an axis other than x or y. All right, let's take a look at number 12C. I've already sketched the graph for you. It's a parabola. It's y equal to 0, x equal to 2. The region that we're revolving this time is this region right in here. We're revolving it about around the line y equal to 8, which is a horizontal axis. It's parallel to the x-axis, so we will be in terms of x. And hopefully you can see that there's definitely some space in between the curve and the axis, so there's going to be a hole in this thing. So let me get rid of that. All right, so there's my axis of revolution. We said there's going to be a hole in this. So since there's going to be a hole, there's going to be a big R of x. Remember, we're in terms of x, and a big R, or a little r of x. Big R is always the distance from the axis of revolution to the outer curve. So I start at the axis of revolution, and I draw to the outer curve. That distance, in this case, is always 8 units long. No matter where I draw the axis of revolution, the distance is 8 units. However, the inside radius is the distance from the axis of revolution to the inner curve. So I'm going to draw it from here to here. Now that's the segment that I want to find the length of. But just like before, I'm going to take that segment and send it all the way over to the x-axis. Keeping in mind that the only part of that segment that I'm trying to keep is this part right here, the red part. That is the radius that I'm trying to define. which means I have to eliminate all of the blue region. So, just like we did before, the entire segment from here to here is 8 units long. I'm trying to eliminate that little blue region, and that blue region is what's bound under the curve 2x squared. So the blue region right here is 2x squared, meaning that the red segment would be 8 units long, the whole thing. Get rid of the blue, 2x squared. So I'm going to accumulate area, pi out front. We're making circles by revolving. The lower bound is an x value of 0. The upper bound is an x value of 2. Big R is 8, and we square it, minus little r. 8 minus 2x squared squared dx. From there, you do your algebra and your arithmetic and your antidifferentiation and find the answer. Okay, let's take a look at the last problem, which is 12D. This time we're taking the exact same region. Did I make that 2x squared? Yeah, I did. All right. Same region. This time we're revolved around the line x equal to 2. And since we're revolved around the line x equal to 2, this is a vertical axis. It's parallel to the y-axis, so we are in terms of y. The region that we're revolving this time is the same region, and notice that this region is completely flush to the axis of revolution. So in this problem, there will be no hole, which means that there will only be one radius, r of y. The radius is the distance from the axis of revolution to the curve. So the radius that we're looking for would be that distance right there. Just like before, send it all the way over to the axis, to the y-axis. The part we want to keep is shaded in red. The part we want to eliminate is highlighted in blue. The entire segment is 2 units long. The blue segment is the distance from the y-axis to the curve. Now remember, the equation was y equal to 2x squared, and I need that in terms of y. So I have y over 2 is equal to x squared, so x is equal to the square root of y over 2. So big R, or excuse me, the radius is 2 units, the whole thing is 2 units long, minus that blue region, the square root of y over 2. There's my pi out front. We're collecting area in terms of y, so we're going to start at a low or a y value of 0. The upper bound we're going to find by taking this x value of 2, substituting it in here to get the corresponding y value, and that gives me a y value of 8. Remember, we're in terms of y. The radius is 2 minus the square root of y over 2 squared dy. That will give me pi from 0 to 8 of 4 minus 2 square root of y over 2 plus y over 2 dy. Now I'm going to take this maybe one more step just to kind of show you what I would do next. I would make this pi from 0 to 8 of 4 minus, I would take the square root of 2 and move it over with the coefficient of 2 in front, taking care of this term right here. I would make this y to the 1/2 power, and then I would make this 1/2 of y dy. In other words, I would just use a little bit of algebra, a little bit of arithmetic to clean this up and make it more friendly to find the antiderivative of, and then from there I think you can handle it. But that's what you would need to do with this particular term to rewrite it to get it ready for antidifferentiation. All right, so hopefully you find this helpful in looking at your homework and studying and preparing for your test.